The last two classes we've been doing like in-class example problems. I just want to go through today the one that we were working on Friday. So if you've been working on it, if you did it over the weekend, you can compare what you did. If you haven't, it's just an example problem. All right, so this is from Friday. We have this beam with a fixed joint at the right and a pin joint at the left. And there is a force of 5,000 newtons. The mass of this beam is 50 kilograms. And we want to calculate the stress tensor at the midpoint. We'll see that there's a little indeterminacy about talking about the midpoint because there's a point force there, but we'll look at it just to the left of the midpoint and just to the right of the midpoint. And at the point P in this cross section, up at the top, where this cross section has a height of 6 centimeters and a width of 3 centimeters.
And what was the length of the beam?
Oh yeah, I didn't say, but it's 2 meters. Okay, so since we're talking right now about indeterminate structures, your first thought is probably, okay, this is an indeterminate structure. But if you just see something, if you're just starting to work on some problem in the wild out of the blue, the first thing you do is the statics. And you don't know it's statically indeterminate till you do that. So we'll start with the statics. So we have RB and we have a couple MB. Over here, we have an unknown force vector RA. And we have our applied 5,000 Newton force. And then we have a weight force. Now that I've chosen the body to isolate, I can treat this as a point force. So it's just going to be 50 times 9.81. So Newton's second law says RAX RAY plus negative 5,000. I'll just lump the weight in there, 490.5. Plus RBX RBY is equal to zeros. So we have a first equation that says RAX plus RBX is equal to 5,000. And a second one that says RAY plus RBY is equal to 490.5. There's no twist, so we only have to do the z component of the moment equation. So we have, I'm going to make my about point here. We have a negative moment of 1 times 490.5 plus 2RBY plus MB is equal to 0. And so our third equation says 2RBY plus MB is equal to 490.5. And this is a system of 3 equations for 5 variables, so we can't solve it. And so we know this is statically indeterminate. And so at this point, we have to calculate the internal loads. Question? Yeah.
Was your about point at B?
Where the red dot is. Do you see that? It's on the left.
Oh, it's on the left. Oh,
yep.
Okay.
Yeah, remember that any couple you just add on and it doesn't matter where it is. Okay, so now what we have to do is use the elongation and the deflection equations to solve, to give us some constraint equations, some extra equations. In order to do those, we have to come up with expressions for the internal loads in terms of variables we've already defined. Otherwise, we're just adding more equations with more variables and we're not getting anywhere, Okay, so how many cuts do we need for this?
2.
2 cuts. Or cut 1 is going to be for x values between 0 and 1. We haven't gotten to the 5,000 Newton horizontal force yet. We do have a weight force, but that's a distributed load. So remember that the distributed load is the total weight divided by the total length. And so we have this distributed load that has a total length of x and a total height of 490.5 divided by 2. And so to make that a point force, it's going to act at the center of the thing, and it's going to be 245.25x is going to be the magnitude of the point force. And then we have our internal loads T, V, and M. Newton's second law says RAX, RAY plus 0, negative 245.25x plus T, negative V is equal to zeros. So we get that T is equal to negative RAX, and V is equal to negative 245.25x plus RAY. And then the moment equation says negative x over 2 times 245.25x plus m minus vx is equal to 0. So m is equal to vx, v times x, plus 122.625 x squared. And so m is equal to negative 245.25 x squared plus ray times x plus 122.625 x squared. And so m is equal to negative 122.625 x squared plus ray times x. You can check the derivative relationships. dm dx is equal to v. Negative dv dx is equal to the distributed load q. So that looks good. And then we'll do our second cut. Anybody have any questions about the first cut? I like these problems even though they go on and on and on because it fits in so much of the stuff that we've done all semester, you know. So cut 2, x goes from 1 to 2. You have RA. This time we have made it to the 5,000 Newton force. And we still have a weight force of 245.25x. And then T, V, and M. So Newton's second law says RAX, RAY plus negative 5,000, 0, plus 0, negative 245.25x plus T negative V is equal to zeros. So T is equal to negative RAX plus 5,000. And V is equal to RAY minus 245.25x. And then the moment equation. Again, my about point is going to be over here at the left. So we have negative 122.625 x squared plus m minus vx is equal to 0. So m is equal to v times x plus 122.625 x squared. So m is equal to RAY times x minus 245.25 x squared plus 122.625 x squared. And so M is equal to, I'm going to reorder it a little bit, negative 122.625 x squared plus RAY times x. Now, what are we going to use this for? Why did we do this? Yeah, now we're going to do displacement. So let's do the elongation first. So the total elongation is, the elongation of the first half plus the elongation of the second half. And what do they have to come out to be equal to?
0.
0, yep, because the two ends are fixed. So we have T1 times 1 over EA plus T2 times 1 over EA has to be equal to 0. Since the cross-sectional area and Young's modulus don't change, this is a case where we don't need these. Sometimes you do need them, but in this case we don't. And so this equation comes out to be negative RAX minus RAX plus 5,000 is equal to 0. And so now we get our third equation for our system. Oh, how many do we have? 3. So this is our fourth. Our fourth equation for our system that says RAX 2RAX is equal to 5,000. Well, might as well solve that. So we have this fourth equation that says RAX is equal to 2,500. I'll treat that as an equation, but when we get into substitution and stuff, that's an answer to one of our variables. So I'll just make a note of that.
And that came from T1 equals negative T2.
That came from this elongation equation setting them equal to 0.
Yeah. So from that you get T1.
So, yeah, so then you can get, right, so I just plugged in from the internal loads, we learned what T was in terms of variables we already had. So T is negative RAX for the first half, and it's this for the second half.
Okay.
Yep.
Yeah.
Any other, yeah.
Just to double check, the one that you're multiplying T by, that's the length of the section.
Yes, that's right. So if that 5,000 Newton force would have been a third of the way along the beam, we would have had a third of the length times T on the first section, plus 2/3 of the length times T on the second section. Yep. But since it's just times 1, I kind of glossed over the algebra. Okay, but now we're getting into, that was like a warm-up, because now we're getting into the deflection, and that's the one that can be a pain. Well, one thing you might notice about this is, even though we have 2 cuts, our bending moment function is the same over the whole thing. And as long as that function is the same, we don't have to break it up into pieces. Okay, so that saves us a little bit of work, because like what's the work that you have, the extra work you have to do if your bending moment function changes at a seam? That's a hint. Remember talking about seams?
have to like use an extra constraint at the seam?
Yeah, two extra constraints. One says that the deflection matches, and one says that the slope of the deflection matches.
And then how that ends up being solved.
Yeah, well, when we get to the boundary conditions for the deflection, we'll talk about the seams too, okay? But in this one, we're not gonna have any seams, so let's just go on. So what we have is that M is equal to E times I times the second derivative with respect to X of the deflection. And so if you integrate, let's put in this bending moment function, negative 122.625 x squared plus RAY times X. So I'll integrate everything and I get that EIV prime is equal to negative 61.31, I don't know how many okay, 61.3125. Oh, nope, I did that wrong. Negative 40.875 x cubed plus RAY over 2 times x squared plus the first constant of integration. Now integrate both sides again. EIV is equal to negative 10.22 x to the fourth plus RAY over 6 x cubed plus C1x plus the second constant of integration, Z2. And now we think about the boundary conditions. And if you had a problem where the function for the bending moment changed, now the boundary conditions include what's happening at the seams. But what you're doing now is you're saying at given X values, we know the value of the deflection. So if you look back at this original thing, at X equals 0, we know that that thing can't deflect. But it can be at an angle. If you imagine like pulling this down, there's nothing in that pig joint that would hold that vertical at all, horizontal at all. And so the only boundary condition we have here is that the deflection is 0. And then over here at X equals 2, we know that deflection is 0. And we also know that deflection prime is equal to 0. Okay? If this was a problem where the bending moment function changed at the middle, we would also have the two things that said deflection, at X equals 1, deflection according to the left function equals deflection according to the right function. We don't know what it is, but they have to match. Does that make sense? And then deflection prime, we don't know what that is either, but we know that those also have to match.
So if you had two functions, you'd have 4 constants of integration.
Yes.
You'd have to run them side by side, and then they'd only be valid. Like
Right.
If you had a constraint on the right endpoint, you have to use your equation that includes that value.
Yeah, that's right.
I remember.
That's right. Okay, so since we're setting these things equal to 0, it doesn't matter that our deflection and our deflection prime are multiplied by constants. So we don't, if v and v prime are equal to 0 somewhere, eiv and eiv prime also are equal to 0 somewhere. So I don't have to mess with dividing by those or anything. Okay, so now we're getting into the boundary conditions. And the easiest ones are always at x equals 0 because all the terms go away except for the constants of integration. So at x equals 0, the deflection has to be equal to 0. So that says 0 plus 0 plus 0 plus c2 has to be equal to 0. And I'm going to, as we go, just continue updating these functions. So this is C2, so the only thing we have to update is EIV, and that's equal to negative 10.22 x to the fourth plus RAY over 6 times x cubed plus C1x. And now we know C2 is equal to 0. Now our second boundary condition will say at x equals 2, let's do the deflection prime first, is equal to 0. So this says negative 40.875 times 2 squared plus RAY over 6 times 2 to the third plus 2C1 is equal to 0.
God, I believe you have the cube of the square backwards.
Yeah, that should be a fourth and third. Yeah. Here we go.
Wait, on C1,
You're what?
should C1 have a 2 on it?
That's the 2 there.
Yeah.
So we're going up to B. Are we doing B or B prime? Because I think the equation is that you did is EIV. Wouldn't it be EIV prime equals?
Oh, V prime. I am using the wrong one. Yeah, sorry. We have to do them both, but okay. So V prime. Thank you. Oh, I was mixing all sorts of stuff up. Okay, let's pretend that never happened. Okay, negative 40.875 times 2 cubed plus RAY over 2 times 2 squared plus C1 is equal to 0. So we get that C1 is equal to positive 327 plus 2RAY. And now I'm going to update my deflection. There's a bunch of orders of ways you can solve this system, but I'm going to use these two boundary conditions to come up with an expression for, well, I'm just going to come up with an extra equation that involves the variables that we have in our original list of variables. So now if I update that deflection, we have EIV is equal to negative 10.22 x to the fourth plus RAY over 6 times x cubed plus 2RAY times x plus 327 times x. And so now we're going to say at x equals 2, the deflection is equal to 0. Oh, yeah.
Should be minus 2RAY.
Yes. Thank you. Okay, that look good? I think so. All right, now deflection. So now we're going to, so we have negative 10.22 times 2 to the fourth plus RAY to the 6 over 6 times 2 to the third minus 2RAY times 2 plus 654 is equal to 0. So negative, nope. Negative 163.52 plus 4/3 RAY minus 4 RAY plus 654 is equal to 0. And so we have negative 8/3 RAY is equal to negative 490.48. And so RAY is equal to 183.93. And what was our last numbered equation? So this is equation 5. So now we can just work through the things we know. Since RAX is 2,500, RBX is also 2,500. And RAY plus RBY is 490.5. So RBY is equal to 306.57. And then last, the moment equation from the statics says 2RBY plus MB is equal to 490.5. So that says that the bending moment is equal to MB is equal to negative 122.64. Newtons, Newton meters. Okay, so what did we do all this for? What's our final goal in this problem?
Stress tensor.
Yeah, we want to come up with a stress tensor. And so now we've gotten to the point where since we have those external loads, we can calculate the internal loads at any point. We couldn't do that before because remember our internal loads are all given as, functions of our external loads. Okay, so now on cut 1, our internal tension is equal to negative RAX, so it's in compression of negative 2,500. Our shear force on cut 1 negative 245.25x plus RAY. So negative 245.25x plus 183.93. And our bending moment on cut 1 is negative 122 negative 122.625 x squared plus they're the same, RAY times x. Plus 183.93x. Okay, and on cut 2, T is equal to positive 2,500. And these two functions are the same. Yes?
This might be a dumb question, but is the shear force the derivative of the moment, the internal moment?
Yeah, as long as you're talking, yes, that's true. So yeah, that's a good observation. I could have just seen it that way. Yep, you're right.
I didn't know if it just looked that way.
As long as you're talking about the functions, just be sure you're not, yeah, right.
Okay.
Okay, so now we got this. And so now, now we can go through calculating the stress tensors. Okay, so the stress tensor due to the tension. So if you're coming to x equals 1 from the left side, the xx element of your stress tensor is equal to negative 2,500 divided by the cross-sectional area and you get negative 1.39 times 10 to the 6. And so that says that the stress tensor due to tension coming from the left side is negative 1.39, I'll just write it in megapascals. Coming from the right side, crash, of course. Okay, so from the right side, the only change is that the internal tension is positive 2,500. And so you have a stress tensor of positive 1.39 megapascals and zeros. Okay. Now shear force. Can anyone notice anything about the shear force that would help the laziest among us here?
Both sides.
It is the same for both sides, and even better than that. For the shear force, we have that shear xy is equal to negative VQ over IB. Q is the area above the point that you're looking at times the distance to the centroid of the area above. How much area is there above the point that we're looking at? Yeah, none. So this Q is equal to 0, so this is 0. Okay, anytime you're calculating a stress due to shear force, it's 0 at the top or the bottom. And it's at its maximum in the middle. Which is why, if you remember, when you calculate shear stress, when you calculate the shear stress due to shear force, for a round cross section, we can only calculate it along the neutral axis, but the good thing is that that happens to be where it's maximum, so it's better than nothing. Yes?
So I forget, is it the distance from the point that you're interested in to the center of the cross section, or is it from the centroid of the area to the cross section? Or Q?
Yeah, I'll draw the picture. So if you're looking at, say this is where you want the value.
Yeah.
It's this area, and the distance is from the neutral axis to the centroid of that area.
Okay.
And now bending moment. This is a normal stress, and it's equal to negative my over I. That area moment of inertia is 1/12 times the base times the height cubed. So that's 5.4 times 10 to the minus 7 meters to the fourth. So this is equal to negative. Let's calculate that bending moment. The bending moment is 61.305. The y value is from the neutral axis to the point you're interested in. The height of the whole thing is 6 centimeters. So from the neutral axis to the top is 3 centimeters. And remember, this is signed. So if we were going below, we'd have a negative value, but here we're going up. So we have a positive 0.03 divided by 5.4 times 10 to the minus 7. And you get positive you get negative 3.41 times 10 to the 6. So the stress tensor due to bending moment is negative 3.41000000. And so now we just have to add these up. At x equals 1 coming from the left side, the total stress tensor is negative 3.41 minus 1.39. And so you get negative 4.80 megapascals. And at x equals 1, coming from the right side, we have a stress tensor of negative 3.41 plus 1.39. So negative 2.02 and zeros. I mean, you can see how much of, I mean, that's well over half of the material probably that we've covered all semester in one problem. And if I'd chosen a point that wasn't at the top, we would have done shear force. So, any questions right now about that?
Yeah, I missed how we got, what changed between coming from the left.
Oh, just remember that when we had different functions for the internal tension, different values coming from the left and the right. So you have to consider those separately. Remember our internal tension was negative 2,500 for cut 1 and positive 2,500 for cut 2.
Yes,
So that's where. Yes,
that's the only thing that changed.
that's the only thing, yep.
So, should we have as many stress tensors as we do segments, I guess?
Yes,
So if you made 2 cuts, you would have 3 stress
right.
tensors?
But you can save a little time if you notice that not all of the internal loads are changing at every cut.
Okay, so it matters where the internal loads change.
Right, that's all that matters. Yep. You just have to take into account all the internal loads. Any other questions? Okay, that's it.